Okay, today, guys, we're going to learn a little bit about reactions that don't fit our typical single replacement, double replacement, synthesis combination, decomposition, or combustion model. We have some reactions that we balanced in our balancing chemical equations last week that didn't really fit well for the description. And I told you at that time that those reactions fell into the category of something called oxidation, reduction, or redox reactions. So, if you have your notes handy, you can see that reactions that are redox would include any reaction that we would normally label single replacement, combination, decomposition, or combustion. Some reactions that don't fit well in one of those categories might also be an example of a redox reaction. But here's the thing: double replacement reactions are never, ever going to be redox reactions because double replacement reactions lack the one thing that all those other reactions have, and that is um, the oxidation numbers of the individual components in the double replacement reaction don't change from the reactant side to the product side. So to actually genuinely be able to distinguish um, a reaction as a redox reaction, you have to be able to assign oxidation numbers to the species in a chemical reactant or product. Okay, so on your little note page here, I have a list of oxidation number rules, and you're going to refer to this at all times when we're kind of assigning oxidation numbers. It's not something I would have you memorize, it's something that I would always let you refer to. Okay, so the oxidation number rules are that free elements always have an oxidation number of zero. So it's just an element from the periodic table. Okay, monoatomic or single element ions have oxidation numbers that's the same as the charge of the ion. Example, aluminum, a single um, monoatomic ion, okay, has an oxidation number of 3 because it's a group 3A nonmetal. Um, Fluorine would have an oxidation number of -1 because it's a group 7A nonmetal, and sodium alone in a compound would have an oxidation value of +1. The oxidation of number of hydrogen in a compound is always +1, except if it's a metal hydride like the compound NaH. Okay, that's a very rare occurrence. So mostly the oxidation number of hydrogen is +1. The oxidation number of oxygen in a compound is -2, with the exception of peroxide compounds like hydrogen peroxide. Okay, when you have a neutral compound, just a regular normal formula, the sum of the oxidation numbers for everything in it add up to 0. And if you have a polyatomic ion, the sum of the oxidation numbers add up to the ionic charge. Okay, so what I would like to do is I would like to actually show you some examples of assigning oxidation number values. Okay, so if you have your note page, you can kind of look along. We're going to assign oxidation number values to this compound, iron 3 phosphate. Okay, this is an electrically neutral compound, so it's going to have an oxidation number value for iron, an oxidation number value for phosphorus, and an oxidation number value for oxygen. And those three oxidation numbers are going to add up to 0 because this is an electrically neutral compound. When I'm assigning oxidation number values to uh, individual atoms, I always start with oxygen. Oxygen itself has a -2 oxidation value. Okay, in this formula, there are 8 oxygens, and each of them have a -2 oxidation value. So in total, oxygen is supplying -16 to the total oxidation value of this particular compound. Now, I always start with oxygen, and if I've got like a formula that's got 3 elements in it, after I assign oxygen, then I go to the first chemical. In this case, it's iron. Okay, iron is a single element ion, and iron has 2 possibilities of charges. It has a possibility of +2 or +3. And from the looks of this compound, that 2 right there is giving us an indication that the normal charge of iron is a positive 2. So I'm going to go ahead and assign its oxidation value as positive 2. Now, in this formula, there are 3 irons, each with a positive 2 value. So overall, iron contributes a positive 6 to the overall oxidation value of this particular compound. Now, our last task is to assign the oxidation value to phosphorus. Okay, I want to point out to you that this 2 on the outside of the parentheses means there are 2 phosphoruses in here. Okay, so whatever we assign as my oxidation value to phosphorus has to multiply by 2 and then add to positive 6 and negative 16 to give me a value of 0. So I am going to assign a positive 5 to the oxidation value of phosphorus. Positive 5 times 2 gives me positive 10. So when I add the contributions to the oxidation values for each of these elements up, 6 plus 10 is 16, added to negative 16 will give me an overall oxidation value of 0. So my oxidation numbers for iron are positive 2, for phosphorus, positive 5, and for oxygen, negative 2. Okay, now I'm going to show you assigning oxidation numbers to a polyatomic ion, which is just a little bit different. Okay, so here's a polyatomic ion you guys should be familiar with. This is the dichromate polyatomic ion. It has a charge of negative 2. Okay, when you are assigning oxidation numbers to an ion, okay, instead of the sum of the oxidation numbers adding up to 0 like it would for a compound, the sum of the oxidation numbers in this case are going to add up to the overall charge of the ion. So we want the oxidation number total to be equivalent to negative 2. Okay, so just like in my previous example, I want to assign oxidation value to the thing that is most stated, which if I've got hydrogen or oxygen, I always want to assign it first. Okay, the normal oxidation value for oxygen is a negative 2. Since this has 7 oxygens in it, and each oxygen has negative 2, oxygen itself will contribute negative 14 to the overall oxidation value for this compound. Now, I'm going to assign the oxidation value to the chromium, but I have to remember that there are 2 chromiums in this formula. So whatever my oxidation value for chromium will be, it has to multiply by 2 and then add to 14 to give me negative 2. So the number that will work here will be a positive 6. 2 times positive 6 will give me positive 12 as an overall contribution from chromium. Positive 12 plus negative 14 will sum up to negative 2. So my oxidation values for chromium are positive 6 and negative 2. Now, you're probably wondering, why on earth would anybody care to kind of look at these oxidation numbers? What's the point? They kind of seem a little random. Well, the reason why we look at oxidation numbers, and we're just kind of doing a little exploration here, is because the oxidation numbers themselves can indicate whether a reaction that we have is actually a redox reaction, because you're going to see a change in oxidation numbers through the course of a chemical reaction. So let me tell you a little bit about oxidation reduction reactions. Oxidation reduction reactions are reactions that involve 2 different chemical processes occurring: oxidation and reduction. They occur together. You'll have one species in your reaction that will undergo oxidation, in which the atoms or the ions increase in oxidation state. Okay, by that I mean when something undergoes oxidation, it's actually going to donate electrons to the thing it's reacting with. Now, another species must undergo reduction, that is, accepting the electrons from the thing that is donating it. So we have one component of the reaction that's getting rid of excess electrons and one component that is actually taking up excess electrons. Okay, so the easy way to remember this is with the mnemonic of oil rig or Leo Ger. If the species that you're looking at displays a loss of electrons, it's undergone oxidation. And if it experiences a gain in electrons, Ger, then it is reduction. Okay, so I'm going to show you two examples of oxidation and reduction um, so that we can kind of map this here, and this goes along with your notes. Okay, so in this little schematic reaction of a double replacement reaction, or excuse me, single replacement reaction, okay, I already have the oxidation numbers for copper 2 aqueous and zinc aqueous. Okay, I have the independent elements, zinc and copper. The oxidation values for free elements are 0. So if I want to map this particular reaction, if I look at how the oxidation number changed from the reactant side to product side, I started off with a positive 2 charge on the copper, and I ended up with a 0 oxidation value. Okay, if you go back and you think about what the signs positive and negative mean, you may recollect that if something has a positive charge, it has fewer electrons than it's supposed to have. Okay, so if I went from fewer electrons than I'm supposed to have to having exactly the right amount, I would have had to gain electrons. So this component is gaining electrons. And anytime you gain electrons, the gain of electrons is indicating that this species underwent reduction. Now, zinc went from a 0 oxidation state to a positive 2. Okay, 0 means you have exactly the right amount of electrons in it that you're supposed to have. If you have a positive charge, you have fewer electrons in it than you're supposed to have. So zinc moved from a 0 to a positive 2, which meant this underwent a loss of electrons. So this is indicating that oxidation occurred. So since this particular reaction has both a gain of electrons by one species and a loss of electrons by another, I know that it's a redox reaction. Now, to give you a second example with a more fully written set of reactions, this was a reaction that you balanced on homework 4. This one doesn't fit our identifications of single replacement, double replacement, combustion, synthesis, decomposition very easily. Okay, on the day that we discussed this question, I said that it was most like a combustion reaction, or at least a single replacement, but it's not like a double replacement at all. And here's how I can tell. Okay, if I go through and assign oxidation numbers to each of the individuals, the oxygen is a free element, so it is going to have a 0 oxidation state. If I assign oxidation numbers to this species, hydrogen normally has a +1 oxidation state. Okay, if I add the sum of the oxidation numbers together for this compound, it should add up to 0. So if I have a +3 contributed by the hydrogen, then the nitrogen must have a -3 oxidation value on this side. The sum of the oxidation numbers in NO must also add up to 0. Oxidation value for nitrogen is normally -2, which means that the nitrogen here should have a +2 oxidation value. In water, the sum of the oxidation numbers must also add up to 0. Okay, oxygen's oxidation value is normally -2. Since there are 2 hydrogens, each hydrogen must have a +1 oxidation value in order for the sum of the oxidation numbers to add up to 0. Now I have all the oxidation number values assigned, okay, for this particular reaction. And as you can see, for going from the reactant side to the product side, the oxidation value for nitrogen changed from a -3, that is having extra electrons, 3 extra electrons, to going to a positive 2, having a deficit of 2 electrons. So going from nitrogen from the reactant side to the product side, I'm showing a loss of electrons. Now, if I look at oxygen going from the reactant side to the product side, oxygen on the reactant side had a 0 oxidation state. To the product side, it had a -2 oxidation state. So I went from having the exact right amount of electrons that oxygen is supposed to having extra electrons. So oxygen would have had to gain electrons. Since I have oxidation numbers changing where I have something losing valence electron and something gaining valence electrons, I know that oxidation reduction has actually occurred with this reaction. Since I lost electrons here, loss of electrons is always associated with oxidation. So that part underwent oxidation. Gain of electrons always goes along with reduction. Now, we won't spend a lot of time pondering oxidation reduction, but I wanted to introduce the idea to you.